Hello, this is Sun Xing. You're watching my final presentation on KDD Cup 99 project. First, let me address the problem. We're detecting network intrusion here. And this problem is often understood as a classification problem. What we have here is a training data with 41 features and one class label. And we're trying to use that to build a model and then try to test the model on the testing data to see if it can actually classify the visits as different attacks and normal visits. But if you look at the problem again, you will find that it is different to what we call classification usually. I will talk about it later. First, let's look at the dataset. We're using the KDD Cup 99 dataset. It has several problems. People pointed out that it has duplicated data, it has random parts of the training data in testing data, and it also the training data and testing data are not sampled from the same distribution, which I think is the biggest problem here. To address these problems, people have developed different datasets to improve the original KDD dataset. One of them is the NSL KDD. It selects records from the KDD to build the dataset, and it intentionally increased the difficulty by using misclassified data from the KDD dataset. And it also removes duplicate. However, this dataset is not selected in this project because I think that the rationale of this manipulation are not properly justified. For example, you can't just remove duplicate from the training data because duplicates does contain information. For instance, it affects the distribution of classes in the training data. So to pick a baseline classifier, since we want to get the kappa statistics, we use randomly generated result as the baseline classifier result. The result are the probability of assigning an instance to a class is equal to the frequency percentage of the class in the training set. So I believe this avoids the problem of random guessing. And here I picked two models for classification. The first one is naive Bayes, and the second one is decision tree using J48. The reason why I use these two models is that the features in the data has different types. They have categorical feature and also numerical features. If we're going to use classifiers such as SVM, we need to convert the categorical features to numerical features. And we will also need to at least normalize the data. This itself is a lot of work to do. But now what I really want to do is to get some reasonable models and get the result as fast as possible. That's why I choose these two methods. And here are the results. As you can see, the naive Bayes accuracy is not a lot better than the baseline. But what we have with the decision tree, it achieves 97% accuracy, which is quite amazing. But before we say that the model is good enough, we need to look at the confusion matrix. And here's the confusion matrix for random baseline. And this one is for naive Bayes. As you can see in the accuracy table, naive Bayes does not perform very well. You can see that it misclassified most of the normal visit. And this is the decision tree confusion matrix. It looks quite good, but for many of the classes, the classification accuracy is very low, and it does not affect the accuracy only because the number of instances belonging to that attack type is not a lot. What we need here is a better way to evaluate the models than accuracy, and it should be easier to understand than the confusion matrix. So in this project, I would like to propose a new evaluation measure. First, let me talk about the assumption I made in this task. We want to detect network intrusion. In order to detect that, we only care about the model's ability to detect a certain class of attack as not normal. We don't care if Neptune is classified as a Smurf or a DOS is classified as a probing attack. The second assumption I would like to make is that if a model fails to detect one class of attack, it is bad. If the model treats normal visit as one of the class of attacks, it is also bad. And the third assumption is that we only care about how good our model can perform on the worst type of attack. Imagine if we have a great model that performs perfect on all kinds of attack except one. The hacker can exploit that to use that kind of attack to attack our system, and this means our models are vulnerable. So we need to make sure our models perform well on the worst type of attack. According to the assumptions, I would like to propose an evaluation measure to evaluate the model for network intrusion detection. You can see the formula here. You can imagine the F as the F score for an attack against the normal visit. And the I here represents the type of the attack. Pij is a number. Pij is a number of instances from class that is actually from class J and predicted as I. The intrusion score is high when the precision and recall is high for getting the normal visit against all kinds of attacks. And we use the intrusion score to evaluate the models that we have built. Well, the accuracy of naive Bayes classifier is not significantly higher than the random baseline. You can see that the intrusion score shows that it is better. And our best classifier here is still decision tree. One interesting thing you should notice is that the corresponding class of the intrusion score is R2L for our classifiers. This is probably because that in training data, R2L type attack appears 100 times on average in the total 4 million instances. This suggests that R2L type of attack may suffer from unbalanced class distribution in the training set. And the next step, we're going to improve the classifier by solving this problem. Here I would like to propose two methods to improve our models, specifically improve the intrusion score by solving the problem of unbalanced training data. The first one is based on the decision tree classifier. Instead of directly using the training data to train one decision tree classifier, we can resample several balanced datasets, use them to train several decision tree classifier, and then use this classifier as ensemble to build our final classifier. The second method is based on the naive Bayes classifier. We can exploit the generative nature of naive Bayes classifier and solve the unbalanced dataset problem by directly ignore the class prior because the class prior is not informative here. And what we will have is an extremely naive and not Bayesian classifier, which the formula is shown here. And here there are three things that I would like to note. The first one is that both of the two improvements can be easily written in the MapReduce paradigm since they are embarrassingly parallel to some degree. For example, for the resample DT ensemble, we can have the different classifier trained and test at different mappers without exchanging data, and then use the result to output the result to the reducer and train a classifier to combine all the results and then use that to classify the training data. For the second classifier, since the attributes are assumed conditional independence, we can assign one attribute to one mapper and let it to calculate the probability for this specific attribute for different class, and then just output the result to the reducer, and then the reducer can combine all the features and give us a classification result. The second thing to note is that we cannot get kappa statistics of these two models from our original baseline because our original baseline is generated using the class distribution in the training data. But our two models here does not utilize the class distribution in the training data. The third thing to note is that our improved models are trained in a way to overcome the problem caused by unbalanced data, rather than to improve the intrusion score. So we're not using these improvements to specifically improve the intrusion score. If there are any improvement on the intrusion score, they can be considered as desirable side effect. And here, let's look at the improved classifier result. These are the confusion matrix. And now let's look at the scores. These are the final results. Interestingly, the modified naive Bayes have higher accuracy and lower intrusion score. To look at why this happened, let's go back to the confusion matrices. This is the confusion matrix for naive Bayes. As you can see, the normal visits, most of them are classified as other class R2L and probe instead of classified as normal. And in the modified naive Bayes, there are more normal visits correctly classified, but the normal visits that are classified as R2L also increases. And R2L is the type of attacks that is causing the intrusion score, that is has the lowest F value. So right here, the problem of having more R2 normal visits classified as R2L should be the problem of this lower intrusion score. And when you see the resample DT, you can see that the intrusion score actually improves by 0.02%. And when you look back to the at the confusion matrix, you can see that comparing this one and the previous one, if you look at the details, you can see that the second one is actually more strict, which means that more normal visits are classified as attacks, and very few normal visits, except R2L, are classified as attacks, are not classified as normal. From the result, you can also see that the corresponding class for the intrusion score for all of our classifiers are from our R2L attack. This suggests that the problem of classifying R2L against normal visit is not caused by unbalanced dataset itself. It should be caused by the nature of R2L itself. So we probably need to have a more complicated model to improve the intrusion score instead of improving the classifier on the level of samples. And these are the things that I have done in this project. Let's have a brief review. I analyze the KDD datasets and choose to use the original KDD dataset. And then I generated my baseline for getting the kappa statistics. And then I chose decision tree and naive Bayes as my original model. I tested the results and I did some preliminary analysis. And then comes the exciting part of the project. I proposed a new evaluation measure, which is intrusion score for this specific task of detecting network intrusion. And then I proposed two ways to solve the problem of unbalanced dataset. I analyze the result of the two new models and then evaluate these models. And now let's discuss one of the further direction of the project. In the future, we can detect the attack of unseen types. I didn't do this in this project because many of the unseen class have very few instances, and the intrusion score will be very unreliable with such limited data. But once we have enough data, I believe we can approach this problem easily. I would like to propose several ways to do that. First, we need to use the intrusion score all the time because first, it correctly reflects the ability of the model to protect the system from intrusion. And second, the score works even when the model cannot classify some of the classes. You can still calculate a score for unseen classes as long as you know the class label in the testing data. You don't even have a model. You even need to have a model that can classify these unseen classes. And the worst class is highly possible to be one of the unseen class because it is not trained within the information is not in the model. To start classifying this unseen class, we can look at the classification confidence of the instances. We can set up a threshold. When the prediction confidence is below a certain threshold, we can mark the instance as unknown attack instead of the original predicted class. To further approach this problem, we need to use some unsupervised learning techniques, and I believe clustering techniques will be very helpful. That's the end of my presentation. Thank you for watching.